Hi students, today we are going to do some lecture lessons. Okay, so you remember that first part of the lesson already covered. Today we will be covering the electric field due to point charge, electric field lines. Okay, you remember electric charge and conservation of charge already covered in previous videos. Okay, can we go to the video now? So first topic we will take electric field. Okay, what is exactly electric field means? This is something similar to the magnetic field. Okay, an electric field is the region of space surrounding electrically charged particles. Okay, where a force is exerted on other electrically charged objects, exactly like a magnetic field. And in the case of magnetic field, you remember field lines start from north pole, right? So in the case of electric field lines, they start from positive charge and end at negative charge. And in the case of negative charge, it starts from infinity and reach the negative charge. When we talk about the electric field intensity, this is actually the strength of the electric field at that point. Okay, so it is defined as the force experienced by unit positive charge placed at that point. So there is an equation for electric field. How to do that one is just to follow this statement. What is that statement is force experienced by unit positive test charge or unit positive charge. So we can understand it step by step. So you remember, in the previous lessons we covered Coulomb's law. So according to Coulomb's law, force on test charge Q0 due to a point charge capital letter Q is, let me draw a diagram first. So you can see there capital letter Q is there. At a distance R, there is a point P where test charge Q0 is placed. I marked there capital letter F, that is the force away, because both are positive charges. Okay. So as per Coulomb's law, we can write F is equal to 1 by 4 pi epsilon 0 Q0, actually Q1 Q2, right, divided by R square. Here the Q1 Q2 are, first charge is capital letter Q, second charge is Q0. And what is the definition of electric field? Just now I told, right? What is that one? Force experienced by a charge, test charge. So by definition we can write E is equal to force divided by Q0. So we can write the previous equation now in the place of F now. So what is that? 1 by 4 pi epsilon 0 Q0 divided by R square. Now that Q0 is left, so we have to write that also in the denominator Q0. Now we can cancel this numerator and denominator Q0 I am cutting now. Okay, done. And unit vector I added at the end, that for direction purpose. Okay, so where R cap, you know the R cap, right? That is a unit vector. R cap is the unit vector. Okay, unit vector. And if you talk about which direction will be, it will be directed from capital letter Q to Q0, small letter Q0. Okay. Okay, just note down these points, this equation. Okay, F is equal to, E is equal to F by Q. Now we are going to see the next part, that is in the syllabus. Second part we want to write. Before that one we have to write the SI unit. SI unit of the electric field is, look into the equation, you can write very easily. Numerator force, that is Newton. Denominator charge, that is Coulomb. So we can write N by C or N C raised to minus 1. Okay. Next thing is electric field due to a system of charges. A similar topic we did before for Coulomb's law. Force due to multiple charges. It's almost a similar concept here. Here consider a system of charges Q1, Q2, Q3 up to Qn with the position vectors R1, R2, R3 like up to Rn we can say. Okay. So consider a point P is there and there is a charge Q1 is there at a distance R1 we can say. Okay, position vector R1. So what will be the direction of electric field at that point is, that is marking here with the blue color, you can see that is the field due to first charge. So I am marking that is Q1. One more charge I am adding, that is charge Q2, which is at a distance position vector R2 from the point P, and the field produced due to that one is E2. Okay, E2. Like you can mark any number of charges. Let me go with the third one, then I will go to the Qn. So a third charge Q3 is there at a disposition vector R3, and the field produced due to that one is E3. Okay, one more we can label, because in our theory statement we used up to Rn. So assume this charge is Qn at a position vector Rn. Okay, and the electric field produced due to that Qn is, what you can write, En. That's all. This is the time we are going to use superposition principle. We used before that one. Superposition principle is nothing. Total will be the sum of individual, basically. Yeah. So the electric field intensity at a point P due to a system of charges is the vector sum of the electric fields at the point due to individual charges. Now we have too many electric fields due to many charges. So if you want, you can write more steps, or if you want to use shortcut, you can write only E1, E2, E3, etc. As this is a lesson explanation, let me write electric field at point P due to Q1 is E1 is equal to K, you know, yeah, 1 by 4 pi epsilon 0, K Q1 by R square place we can write position vector. Okay, so modulus of position vector R1 square unit vector R1 cap. Similarly, for the second charge, we can write the same statement. Electric field at point P due to Q2 is E2 is equal to, in the place of 1 by 4 pi epsilon 0, K Q2 divided by modulus of R2 square and the unit vector R2. Okay, done. You can repeat the same statement for third charge, fourth charge, nth charge. So let me write here similarly. For E3 we can write K Q3 modulus of R3 square R3 cap. I write the last one, En is equal to K Qn divided by modulus of Rn square Rn cap. So what we said in the statement, total electric field at the point P will be the vector sum of individual electric field. So here total electric field at point P is equal to, we can write like a capital letter E, total you can write, or just E you can write. E is equal to E1 plus E2 plus E3 plus up to the last one En. Now substitute the value of E1, E2, E3, etc. So K Q1 divided by modulus of R1 square R1 cap plus K Q2 divided by modulus of R2 square R2 cap plus, we can write the last one now. Okay, En, that is K Qn divided by modulus of Rn square Rn cap. Can you see anything common in this expression? I can see that K is common. So let me write K outside, then use summation symbol. I is equal to, see the Q1 value up to Qn, right? So I is equal to 1 to n. So wherever the number coming, replace the number with the I. So Qi divided by Ri modulus Ri square Ri cap. This is the final expression for total electric field at a point due to multiple charges. Got it? Now we are going to see another one small topic, not a very serious topic. that is electric field lines. Some idea you have about the field lines, but not electric field lines, magnetic field lines. In grade 10 you studied. What is that one is? An electric field lines is a curve drawn in such a way that the tangent to it at each point is the direction of net field at that point. Okay, just have a look into the statement. So electric field lines are actually imaginary field lines. And in the previous diagram you saw that they start from positive and end at negative. Yeah. So some more statement I added here for reference purpose. The magnitude of the field is represented by the density of field lines. What is that meaning? More field lines, more strength you can expect. You remember a magnetic field, strength of the magnetic field is more at the poles because more field line density appears near the poles. Similarly, electric field lines. Okay. So we can see about a few more points about that one, that is few properties of electric field lines. One property is electric field lines are continuous curve. Okay. They start from a positively charged body and end at a negatively charged body. Okay, or in simple sentence, they start from positive and end at negative. That's fine. Okay. Now we can see the point number 2. Okay. If there is a single charge, then the field lines may start or end at infinity. What is that meaning? If you have a positive charge, then field lines start from positive and at infinity. If you have a negative charge, isolated we are talking single one. In the case of negative charge, field lines start from infinity and end at this negative charge. So we can draw field lines due to a positive charge and negative charge here. The first one, the red one, is the electric field lines due to a positive charge. This is the one what I am drawing is electric field lines due to a negative charge. So the direction will be, in the case of positive charge, away from that. In the case of negative charge, towards it. Okay. This was there in the board examination, 1 mark question. Draw the field lines due to isolated positive charge. That is the first one. Isolated negative charge. That is the second one. Then for a dipole, what is that one? Equal and unlike charges separated by a small distance. We will study in the next topic. Okay. So right now you consider like one equal and opposite charges. Then field lines will be like this one. Start from positive and end at negative. Okay. Like this you can draw. And for the this side, left side, it go like this one. Okay. And similarly do for the negative side also. But remember, for negative side, do the arrow mark towards the charge. Simple, right? Same copy is there in the textbook. You can refer the textbook also for all types of field lines. Okay, till now everything fine. In the previous videos it was too fast. Too fast means some students said like, can you do it little bit slowly? We are taking time to digest it. Okay, another one point is, no electric field lines exist inside the charged body. Thus, electrostatic field lines do not form continuous closed loops. In the case of magnet, you remember, they pass through the magnet. So, they form the closed loops, continuous closed loops. But in the case of this one, no formation. The magnetic field lines are continuous. You remember the magnetic field lines due to a bar magnet. There you remember this. Okay. And tangent to the electric field lines at any point gives the direction of electric field intensity at that point. That means if you have an electric field line curve and if you want to find the direction of that one, then just draw a tangent to that line, you will get the direction of electric field lines. Okay. Okay students, thank you. Have a nice day.